We did small routing before, but you may not know that it is called routing. So I'm going to demonstrate or explain that and also demonstrate to you for you to see what we're talking about. So most of the time when you hear routing and switching, that is the backbone or the bedrock of everything in CCNA or in networking. Routing and switching. Routing and switching. We've been doing a lot of switching. Most of the things we did with switch, we refer to those things as switching stuff. And then anything that has to do with router is also referred to as routing stuff. But right from today, in today's class, we want to dive deeper into the routing, into the word of routing, and let's see what this routing is all about. So module 14 is talking about routing concept. So what are the things we have to talk about here? We'll talk about path determination. That is to talk about how the router determines the best path to the destination. I will talk about packet forwarding. I'm not going to do reveal of basic router configuration. I will just go straight into the configuration. We've done router configuration. That will waste time. Then I will talk about routing table, IP routing table, and we'll talk about static and dynamic routing. Those are the objectives. So it's a long journey today. We may spend like 2 hours today, maybe 1.5 hours, but it's a long journey. So let's see how far we can go. So I decided to have a just kind of a foundation, give you guys foundation about what this thing is all about. You know, one of the labs we did when we built basic LAN, basic local area network. If you remember, we had one LAN here. Computers are connected. We call this one LAN A. Then we had another LAN. And then we call this one LAN B. And then I now brought in a router to link LAN A to LAN B.
Oh, excuse me, sir. Recording.
Yes, ma'am.
Please, sir.
Okay, I think I've started the recording. I've started it, ma'am.
Okay, sir.
Thank you. So I linked LAN A to LAN B using a router. If you remember the definition I gave you about a router is a layer 3 device. It's an inter-network device. It makes one network to talk to another network. We've established all of these things. But what I want to establish or point to in today's class is this. If somebody on this side wants to talk to somebody on this side, we know that the message has to pass through the router. How does the router know that the other person is on the other side or the other person is reachable? Recall, we talked about the switch. If computers are connected to the switch, all the switch needs for the computers to be able to talk to themselves is to check its MAC address table. That is where the switch is getting direction from. That is what the switch is using to make a decision. But when it comes to a router, the router has something completely different to make decision. And that is called routing table. Now, we've just been doing our configuration and never mentioned routing table to you. But in today's class, we have to dissect routing table. Routing table is just like a map. You know, for us, we use in some cities in Nigeria, they use GPS. I know in the Western world, GPS functions very well. Even some African countries, the GPS works very well. If you are going to a place and you don't know the place, all you need to do is to punch where you are, the source, and then the destination, and activate the GPS. The GPS is going to give you direction to get to the destination. But the only reason why that can work is because those cities, they've been integrated into a database. And that is where the GPS is getting the information from. If there is any city that is not there or any street, and you try to go to a street that is not in the GPS, GPS cannot help you. It cannot help you. So the same thing with your router. The router has what is called a routing table. The routing table is like the database of all the networks that the router can reach. And any network not in that routing table, the router can reach there. And when we say the router can reach there, it simply means it cannot help you to reach that destination. So if there's a computer on this side now, and it's going to a computer on the other side, this computer belongs to a particular network. Let's give a network address. For instance, let's say this side is 192.168.100.0/24. And this other side is 192.168.101.0/24. So if I give a computer an IP address from that network, this computer is going to be part of this network. And there's a computer here too that will be part of this network. So if this computer needs to talk to this computer here, the only reason they can talk to themselves passing through the router is because the router in its routing table has this network address, It means the router knows how to talk to everybody on the other side. It knows how to forward the message to that destination. But if this destination is not available in the router doesn't know how to push the message to the destination. So we want to dissect the routing table of a router. And we want to talk about how the router builds this routing table. Is it just automatic? No. How does it build the routing table? That is what today's class is all about. Then on Friday, we're going to now finalize it. We're going to go and do more configuration on the router, things that have to do with the routing protocols. So that's just the foundation. So let's go through some story before we do some demonstration. Path determination. Path determination. Two functions of a router. When a router receives an IP packet on one interface, this is a router now. If you receive packet on one interface, because there is a connection on that link. So what happens? It determines which interface to use to forward the packet to the destination. What if the router has, let's say, two different destinations? How will it know where to pass the message through? The message is going to go to a particular destination. So, and this decision the router makes is what we refer to as routing. Because it's possible for a router to have 4 ports, 6 ports, 8 ports. So when the message comes in from one interface, it has to be pushed out of a particular interface, depending on the destination that the message is going to. And how will the router make that decision? It has to look at its routing table, which is like the map, the database in the router, to determine where the message is going to. The interface that the router uses to forward the packet may be the final destination. That is, if you have a switch here now, that probably is going to be the final destination. But why did they put may be the final destination? Sometimes the owner of the message is not on a switch, it's on another segment somewhere. What do I mean by that? Let's assume we have a LAN in Germany, another local area network in France. They belong to the same organization, but in different locations. So computers are here. This is my switch. And we need to link these two local area networks together. This is what we'll be demonstrating next on Friday. We need to link these two local area networks together. It doesn't matter where you are in the world. There's no distance in networking. It's like in the spirit realm, there's no distance in the spirit realm. I will need a router here. I will also need a router here. So this router is in Germany. This router is in France. And we are going to link the two routers together using what we call wide area network technology. There are different types. It depends on the technology you want to go for. We're going to be talking about that. Maybe I'll send some videos ahead that has to do with this one link, wide area network and IP VPN. when I finish the class on Friday, I'll send those. They are in CCNA 3, but I feel it will help you guys because that has always been a challenge for me. When I was a student, it was always a challenge. How will we go to link these two routers together? Because I was always looking at the distance. But in technology, networking, there's no distance. There are technologies out there that can help us to link different locations together within the city, within the country, within the continent, or even intercontinent. You can link them together. So this is my point. If a message is coming from, let's say, this computer here, computer A in Germany, is going to computer B in France. By the time the message gets to the router, it enters through this interface. The router will push it out of this interface. Now, in pushing it out of this interface, that is not the final destination because the computer B is not on that interface. The message has to get to another router before that router now make decision and forward it to the switch, and then the message now goes to get to the final destination. So that is what they are trying to tell you here. The interface that the router uses to forward the packet may be the final destination. It may be, and it may not. So if it is not the final destination, that means there's another router on the way to destination. And sometimes you have more than one router on the way to destination. Sometimes you have 2, sometimes you have 5, sometimes you have 10, sometimes you have 20, depending on where you are going to. Let me give you an example. If I want to go to Google now from where I am right now, how many routers will I pass through? Let me give you an example. I don't think I've ever demonstrated that in this class. There's a command you can use. It's called tracert, www.google.com. Ping command will just tell you, it will just help you to test for connectivity. If you can get to the destination, it should come back and give you a reply. If you can't get to the destination, it will come back and tell you, say, I can't get there. But traceroute command can tell you, when I got to so router, I couldn't go again. And you are going to see where the problem is. So let me hit enter. Now, by putting this tracert, you are going to see different routers that my packet will be passing through. And it's going to be displaying the IP addresses of those routers as it's going from one router to another router to another router to another router until it gets to destination. Sometimes some routers will not display their IP address, probably because they've been configured not to respond to that trace route. The some will definitely give us their details. So now, all the addresses you are seeing on the right, these are different routers. This, my packet is passing through. It's passing through different routers. And it's going to keep on showing you. Ping will just go and come back. The trace route will show you all the routers it's going to pass through on the from source to destination. So you need to be aware of that. So before I can get to google.com, I have to pass through 10 routers before I get to google.com, depending on the website, where the country I'm going to. So this is just a typical example of you trying to go to a particular destination. The interface on that router may not be the final destination. You could have multiple routers on the road to destination. Is this clear? Are you guys with me?
Yes, sir.
Okay, all right. So let me continue. Thank you. So I just needed to show you that so that I can drive that point home. Okay, thank you. Now, take note of this. The interface that the router uses to forward the packet may be the final destination. I just showed you that. Or it may be a network connected to another router that is used to reach the destination network. Because if it's a different network somewhere in another city, then you need another router. Now take note of this. This is very important. This is very important. Each network that a router connects to typically requires a separate interface. This may not always be the case. Each network that a router connects to typically requires a separate interface. So what we are trying to say is this: if I have a router here, there's an interface here, and there's another router in another location, there's another interface here. Most of the time you need connections, direct connection between the two routers. This is what we call point-to-point. And you're going to have the sign called, just to refer to that, it is a wide area network. You're going to watch that, listen to that in my video. It is a wide area network. So one thing you need to know is this: between two routers is a network. Then I can have my local area network here. Let's say this is our LAN A. This is our LAN B. Computers are here. Computers are here. What is the difference between this topology and the one we worked with when we started this router configuration? One is just a local area network that connects two different LAN segments together. They are both in the same environment. We say LAN A, we say LAN B. So they are together in the same environment. But this other one, they are not together in the same environment. It could be in different states, it could be in different cities, it could be in different countries. And that is what we call wide area network. So you need to understand that between two routers is a network. So in this topology now, if I should ask you a question now, how many networks do you have in this topology? This is one network, this is another network, and this is another network. That suggests to you that we need three different networks or subnets to take care of this topology. One for LAN A, one for LAN B, and one for the wide area network. So don't ever forget. I'm going somewhere. The primary function of a router are to determine the best path to forward packets based on information in its routing table and to forward packets to their destination. That is the main job of a router. Router routes, and it will just check its routing table. If the information is not in the routing table, what will it do with the message? It depends. I'm going to talk more on that on Friday. If it has alternative of, okay, if you don't know what to do with this message, forward it to so person with this IP address, so router with this IP address, it will do that. But if the router does not have that kind of message in its routing table, it will just discard the message. It will just throw it away. And then you get pay request timeout because the router doesn't know how to get to that destination. So we're still talking about routing table. Let me go to the routing table and show you. Yeah, let's go through some slides and then we'll now go to the tool right now. We're still talking about routing table. How does the router build this routing table? Because if I bring a router out for you right now, you're not going to see any routing table in the router. Let me show you. Let me show you. I just brought a router out. I am in the router now. In order for me to see the routing table of this router, I will just say show IP route. It's only showing me codes. What are these codes for? I will talk about them now. But nothing. After that code, I'm supposed to see other information. There's no information in the routing table. The codes will always be there. And what are these codes for? It's basically to give you an idea of how the router learns the routing table, how it built the routing table, or what it used to build the routing table. For instance, if you see S in the routing table, it simply means the router got to know about that network through static route. If you see connected, it simply means the router got to know about that network because it's directly connected. If you see R in the routing table, it simply means the router got to know about that network through RIP. These are different ways the router learns, the router builds its routing table. But as it is right now, this router has nothing in its routing table. Let me bring in one of the labs we built before. I can't remember which one is our own, but I'll just load one. Let me load. Okay, this is similar to what we worked with before. I don't know if this is our home, where we had LAN A and LAN B. We use a router to connect two different local area networks together. Now, in this topology right now, we have just two networks. LAN A network and the LAN B network. If I go into this router right now and issue the same command I issued on the other router, show IP route. Watch out. You see the difference between this router and the other router. Watch out. You can see our code. The code is still up there. But under the code, there are some other information. Under gateway of last resort is not set. What are these information? These are the networks the router knows about. The first one I need to look at here, look at this C. The router knows about 192.168.100.0/24. How did he get to know about it? It is directly connected. On which interface? Gigabit 0/0. That is one of our LANs. What about the second C? C simply means directly connected. This is another network. 192.168.101.0/24. It's also directly connected and it's on Gigabit 0/1. These are the two different networks the routers can talk to or can help you to talk to. Anything not in this routing table, the router doesn't know how to get there. What about the L? L is simply talking about the IP address on the interface. It is called local host. So if you go and look at the Gigabit 0/0, we put 192.168.100.1. And if you go and look at the other interface, we put 192.168.101.1. So as we are doing this, the router is building its routing table. And I'm going to show you now at work. So when you first put an IP address on an interface, and the interface is up, the line protocol is up, the router will add the network that that interface belongs to into its routing table. Let's do it fast before we continue. Let's bring in another router, just for the sake of this class now, just to drive this point home. I won't put any computer. I just need to show you how this thing works. So in this segment, let's say 200.100.100.0/24. On the other segment, let me use 192.168.100.0/24. What does that mean? I can pick any of the IP address on this from this address and put on my interface on Gigabit 0/0. That becomes default gateway to people on that LAN on my left. On the other side, I can pick any IP address from 192.168.100.0. That becomes default gateway for people on the other side. So as it is right now, let me go to this router and show you. Let's give this router a name. Do show IP route. You see there's nothing in the routing table, nothing except the codes. Nothing there. Nothing is there. In fact, let me try something. There's a debug command I think I've one use. I don't know if it's debug, I think IP events. I think it's debug IP routing. Let me check this. It may work for us. So now you watch what will happen now. As soon as we go into interface G0/0, IP address. Pick any IP address from that segment, which is the left segment now. Left to me now here. That is on G00 here. Pick an IP address, any IP address there, and put on that interface. Let's say 200.100.100.1 subnet mask. The moment I say no shutdown, if that command is the one I'm thinking, you're going to see the process of the router adding this IP address into its routing table and the network where this address came from. You watch out. You see all this information you see here. It's adding 200. In fact, it started from here. Sorry. Look at it here. Interface gigabit 0/0 added to the routing table. It is directly connected. So what exactly did he add to the routing table? Ali, can you hear me? Somebody said audio lost.
I hear you, sir.
I can hear you. We can hear you.
Network anyway. It says, Dr. Samuel, can you hear me? Can you hear me?
I can hear you, sir.
All right. So, nice name for Wi-Fi, Ali. Thank you. Don't mind me. It's my wife's network. You know, she's doing cybersecurity, so we like working with some of those terminologies. It's all right. So you can see this network, the interface is being added, and once the interface is added, what is added mainly is the network address that interface belongs to. So if I go down now, even the IP address on the interface of the, what do you call it, of the, that's we put on that interface, that is the G0/0, is also added. So if I go back now and say do show IP route, you will see that the router is building the routing table already. So in the routing table, it puts the relay connected network where that IP address came from is there in the routing table. The IP address that is on the interface itself, it's also in the routing table. This is one of the ways the router builds its routing table from directly connected networks. We never talked about this before because we have not reached there. Now we are there, now we have to talk about it. So I can go to the second interface G0/1, and say IP address 192.168.100.1, 255.255.255.0, and say no short. The same thing will happen. So you see that those network will now be in the routing table. I can say show IP route connected. I only want to see the directly connected network. So these are the only two networks that this router can help us reach. Any network not in this routing table, you can't pass through this router to reach the place. What the router will do is you just discard the message. If you send a message to somebody on 192.168.100.2.3.4, when it gets to the router checks the destination IP address. Okay, this person is going to this network. Do I know how to reach that network? If I don't, is there any other person next to me that can reach the network? If there is any other person that can help me to reach the network, I forward the message to the person. If there's no other person that can help me reach the network, then I will get rid of the message because I can't help the person. This is one of the ways the router builds its routing table. So one of the things you need to now learn is you need to be able to dissect the routing table. You need to be able to break down all the information in the routing table. So let's proceed with this. Is this one clear? Let me be sure it's clear before we proceed. I told you it's a long journey today. It's not like the last classes that we had 1 hour, 1 hour plus. Okay. Yeah, people should talk to me. Clear? Thank you, Mrs. Adebimpe. Thank you. So now, why do we need to know most of the things we are, or learn all these things we are learning? As professionals to be, network engineers to be, you cannot just set up things and say it's working and leave the place. What if the things develop problem? How do you fix the problem? It is when you know the way things are supposed to work that you are able to fix the problem when they are not working. If you don't know how things are supposed to work or how things work, when they have problem, you can't fix the problem. You need to understand that. So it's not just good enough. I can set up a router to link 2 LANs together, to link 4 LANs together. No. It's not enough. When you build the LAN, what happens to the router? One of the things the router will do is to build its routing table. And that is what it will use to help to make that decision. So what is routing sources? That is a source of information for the router to build its routing table. We've just explored directly connected. There are others, static routes and dynamic routes, and we're going to be doing this one in the next class. This one we'll demonstrate it. This one until we start CCNA 3 before we can demonstrate it, but I will just mention it. So what is a routing table? A routing table contains a list of routes to known networks. Prefixes and prefix lengths. Prefix is just the network and the subnet mask of the network. And there are 3 major ways that the router can build its routing table. It can build the table through directly connected networks. This is what I just showed you. It can build the table through static routes. We are going to do that in the next class. And it can also build the table through dynamic routes. But either way, the router must know how to get to destination if you want the router to help you to get to destination. When I say want to help the router, to help you. If the router doesn't know how to reach a particular destination, you can't reach the destination. Say for instance now, this is a network here now. And this router has no idea about this network because it's not directly connected. Nobody from this LAN will be able to reach that network. So we need to find a way to inform this router about this network that is not directly connected. It is called a remote network. And this router 2 here, let's call this one router B. Let's call this one router A. Router B is also not directly connected to this network here. We need to find a way to inform router B about that remote network. That is when the 2 LANs can talk to themselves. And that can either be done with static route or dynamic routing protocol. Directly connected, the router, you don't need to do anything. Once you put IP addresses on the interfaces of the router, you are good to go. But what about remote networks? You got to do some other stuff. The source for each route in the table, in the routing table, is identified by a code. Common codes includes the following. I've showed you some example. Like L, that is the address assigned to the interface. C means it's a directly connected network. S means I got to know about this network through static route. O means I got to know about this network through OSPF. We're going to talk about OSPF in the next, when we get to CCNA 3. And then the last one means this route. When you see asterisk, it means this route is a candidate default route. What is the candidate default route? All of these ones will be discussed when we move to another level. Okay. So there are different principles. The router will, 3 routing principles. I think I've explained some of them, if not all. But let me just go through this. There are 3 routing table principles as described in the table. These are issues that are addressed by the proper configuration of dynamic routing protocol or static route on all other routers between source and destination. Number 1, every router makes its own decision alone based on the information it has in its own routing table. I've explained that one. Number 2, the information in a routing table of one router does not necessarily match the routing table of another router. Of course, now most of the time you don't have them the same. The information in the routing table, they will have similarities, but they can never be the same. What I'm going to have in router 1, in the routing table of router A, will be completely different from router B. And we're going to see that when we come to wide area network configuration in the last class. Routing information about a path does not provide return routing information. I can only explain this by demonstrating. Just take note of this. Ping or communication is a two-way thing. The fact that somebody can go to this destination does not mean that the destination can reply back. That is what this is talking about. And I'm going to demonstrate it for you when we get to, that is static routing. So you need to always have, yes, Dr. Samuel. Please go ahead. Doctor, you raise up your hand?
Yes, I raised up my hand, but I forgot I've not unmuted. I'm
Okay,
looking at the example for the second routing table principle. I don't understand it. It says because R1 has a route in its routing table to a network through R2, does not mean R2 knows about that same network. How is that possible? If I know somebody through somebody else, how would that person not know that person I know?
Are you talking about the second principle?
Yes, that example that they used to illustrate.
Okay, you are looking at their own example.
Yes, it doesn't
Okay,
make sense.
let me read. Just because R1 has a route in its routing table to a network on the internet via R2, that does not mean that R2 knows about the same network. It is very possible. Let me give you an example.
Okay.
I have a router. I know the way you are thinking. You are thinking about directly connected network. Let's say this network here is 200.100.100.0/24. It is, let's name this router. Let's say router A, router B, router C. Don't worry, when we do this labs, you are going to understand these things better. Now, the only router that knows about this network here is router C because it's directly connected. Do you agree with me?
Yes, sir.
You agree, sir?
Yes, sir.
Now, for somebody here, let's say a computer here, PC A, to talk to anybody on that network here, I have to manually or dynamically inform router A about this network.
Okay.
I can do that, inform this router about this network, and exclude this guy and this guy doesn't know about this network. And that is going to create what they call, is it gotcha they call it, gotcha or something like that in networking. As in there's a loophole somewhere. The fact that this one knows about that destination and this one doesn't know about that destination, this guy cannot help me to get to the destination because I need to rely on router B to get to the destination. And if router B doesn't know about the destination, there's nothing he can do to help me. It will just discard the packet. Do you understand?
Yes.
So it is possible. So that is why when you're doing your configuration, when things are not working the way they're supposed to work, I have to come and find out, okay, I'm not getting to the destination. Does this router know about that destination? Yes. The one that is supposed to help us to get it, does he also know about that destination? I will check his routing table before I decide. And by the time we come to the configuration, it is not enough for these routers to also know about the destination. This guy that will bring the reply back needs to also know about this network here. And the guy that is going to pass through also needs to know about this network. That is the meaning of this last statement here. And the best way is to just demonstrate it. Is it clear, doctor?
Yes, sir. I get it now.
Okay, good. So can I proceed?
Yes, you can.
Okay. Any other question before I proceed? Let me just give room for question. To this class, there's no rushing. We're going to spend almost 2 hours in this class. Just trying to lay the foundation for next class. I must get this foundation right. Okay. I believe there's no question. So when you enter your routing table, there are so different things you're going to see in the routing table. Look at them here. The first one is just referring to the route source, how we get to know about the information. In the other one, we saw C. Here is showing us O. O means OSPF. The second information is talking about the destination network, prefix and prefix length. It's telling us about the network and the slash of the network. The third information is talking about the administrative distance, just this one here. What is administrative distance? We are coming there. The fourth one here is talking about metric. What is metric? We're also going to talk about metric. But look at the fifth one. Sometimes you have this. We don't have this in our output for now. It simply means the destination I'm trying to reach is not directly connected to me. I can reach it through this guy. That is the next router on my way to destination. That is called next up. The next router on my way to destination. Then number 6, route timestamps. How long I've known about this network. I've learned about this network. I learned about it 13 minutes ago. And then the last part is the exit interface. The interface on me as a router to get the message out. You need to know all this. And that's for IPv4. For IPv6 is similar, but it's shorter. The route source, the destination network, administrative distance, the metric, the next up, that is the next router on the road, and the exit interface to go to the destination. So anytime you issue show IP route, you must know what you are looking for inside that IP. You must be able to interpret that table. That's the point. And we're going to come to that again when we come to our static route in the next class. So if you go to my home right now, you see that I don't have all these outputs here because I don't have a remote network in my in my topology. I only have directly connected. Show IP route. You see that I have directly connected. Fine, let me put show IP route connected. Look at my own output. I have the route source. I have the network. That is the prefix, network prefix, and then the prefix length. Then my own is telling me that it is directly connected. But in the next class, I'm going to rebuild another LAN and assume that that LAN is in another location entirely, in another city or in another country. And then we'll be able to see that output in our own also. We'll talk about directly connected network. When you see C, it simply means directly connected. And when you see that L, that is the IP address that is put on that interface. And the reason why you see /32 days because it's just referring to that IP address, not about the subnet the address came from. You know, the 32-bit, we're concerned about the 32 bits. Now, directly connected network is interface is very important because if that interface is down, we can't know about remote networks. Supposing this interface is down now, it will not have any connection or communication with the other router. So you can't know about any other remote network. And if this interface is down, we can't learn about this network. So we must first of all have directly connected interface or networks first in the routing table. You will always have C in the routing table before you have other things like your static route or dynamic route. You must always have C. That is very important. And you can have more than one because it's possible for me to be connected to another router again, through another interface, going to another destination, maybe another router, through another interface, going to another destination. And so if somebody here wants to send a message, it gets to this router, the router needs to check his routing table to find out, am I forwarding it through this place or pushing it here or pushing it here? Based on the information it has learned from the other routers, it knows where the destination network is, and then it can decide where to send the message to. And that is a routing for you. So what is this static route all about? I'm not going to demonstrate that. I will just try to explain it. Anytime you hear static route, there are 3 different types of static route. We have static, and we have static default route. We have static host route, and then we have the standard static route. We are going to talk about those ones in next class. But anytime you hear about static route, what you should just know is this. You are the one telling the router manually about the remote networks. Let's say this network is 200.100.100.0/24. This one is 200.100.101.0/24. And don't forget, this link is a network also, 200.100.102.0/24. Most of the time, we have /30 on our one link. So router A is directly connected to two networks, this network and this network. Those are the only two networks it knows about. So what happened to this? Let's call this one LAN C, and let's call this one LAN A. So how will the router A reach LAN C when it's not directly connected to LAN C? Hi, as the network administrator, I have to go to this router manually and tell this router, in case you have message for anybody with this on this network. Or let me put it this way, there is a network that is remote to you. It's not directly connected to you. And in case you have, this is a slash, that is the prefix length. And in case you have message for anybody on that network, forward the message to router B. That means I will go to router A and tell router A manually, what am I doing? What am I configuring? I'm configuring static route. I am telling the router manually. That is static standard route now. There are others. I am telling the router manually about that network that is not directly connected. And I will do the same thing to router B. Go to router B and inform router B there is a network somewhere here that is not directly connected to you. In case you have a message for anybody on that network, just send the message to router A. So the two routers now synchronize, and they know that they have remote networks and they can help themselves to get to those remote networks. And we do this manually when we are doing static route. But if we are not doing static route, then it's not manual, because we can also do what is it called? Dynamic. But for now, we are doing only static. Is that clear to us, please? Okay. Thank you. So that's what static route is all about. So just, I can't start it today and do justice to it. That's what we're going to do the whole of on Friday. We'll go to configure static route. And please, I've sent the videos I had before. So if you guys time, you please listen to those videos. After directly connected interfaces are configured and are added to the table, we must start with directly connected first. Static or dynamic routing can be implemented for accessing, look at it here, remote networks. Standard routes, static route rather, are manually configured. Who does the configuration? The administrator. They define an explicit path between two networking devices. They are not automatically updated and must be manually reconfigured if the network topology changes. That is the problem with static route. You must always update the router manually. Network is done, yank it off. Network is back, put it back. Network is done, yank it off. Network is back, put it back. That is why dynamic routing protocol is better. They update themselves. They yank off network that is no longer available, and they put it back when it is available. And that we're going to see when we get to CCNA 3. But for small network, static route works perfectly. So static routing has three primary uses. Number one, it provides ease of routing table maintenance in smaller networks that are not expected to grow significantly. I just told you that. Number two, it uses a single default route to represent a path to any network that does not have a specific match with another route in the routing table. What is this one all about? I told you what I configured is called static standard route or standard static route. I think it's standard static route. There is another one that is called default route, and that is the one we use on any router that is connected to the internet. Let me give you an example. I'm not going to do configuration, I'll just explain. Let's say this is my router. Let's say CCNA class, this is our router. We have a local area network here. We are all here connected to this switch. And we need internet connection. We connect this router to ISP. So now we are talking about routing table. This CCNA router knows about this network that is directly connected to ISP. And it also knows about our LAN. So what happened when we want to go to Google? You want to go to Yahoo. You want to go to Facebook. You want to go to Instagram. You want to go to Amazon. You want to go to AliExpress. All kinds of websites out there. And those are different networks out there. How many of those networks will I have to tell my router? If you are going to Google, send a message to ISP. If you are going to Yahoo, send a message to ISP. If you are going to Facebook, send a message to ISP. If you are going to all kinds of networks out there in millions, we cannot do that. And so instead of doing that, we'll just tell the router, if you get message for any network you don't know about, just send it to the ISP. And that is what the default route does. We're going to also learn how to configure that. We're not going to be specific about this is Google's network address, this is Facebook network, this is Yahoo's network, this is Amazon's network. No. We're just going to say, you have somebody that can help you here. The service provider has all the networks to all those websites. He knows how to get there. We don't need to reinvent the wheel here. We just tell this router, if anybody is trying to go to a network you don't know about, just send it to the ISP. So when you look at it there, it is routing table. You are going to Google. Google is, let's say, 129.something, and it doesn't have it in its routing table. It just push the message to ISP. And that is called a default route. It simply means one network address in the routing table to any networks, because we have a service provider that is going to help us to get to destination. And that is what we do on any red network router that is connected to the service provider. We call it edge network. Edge router. So on our router that is talking to our ISP, we always configure default routes. Default route. But if it's just within the organization where we want to just point to the networks we have, we configure static standard routes. Static standard routes, meaning we point to the networks that we want to inform our router about. But if it is internet connection, we just tell the router any network with any subnet mask, forward it to the service provider. And look at it here. Default routes are used to send traffic to any destination beyond the next upstream router. The service provider is also connected to other service providers, and they share information between themselves. So it routes to and fro from stub network. What is a sub network? Any network that has one leg out, or one leg in from the outside world. A stub network is a network accessed by a single route, and the router has only one neighbor. That is a stub network. So most of the time we configure this default route on an edge router. Take note of that. All this configuration will be done next class. So you are going to see some of the explain the way it is done here. I will just point to one and just leave it like that. Look at now, router 1 is directly connected to this network, also directly connected to this network, but doesn't know about this network here. So we have to inform router 1 manually about this network. And what is the command? Look at what they did now on router 1 and global configuration mode. IP route that remote network with its subnet mask, we say forward it to this router, which is this IP address. Sorry, yeah, that's this, which is this router here. That is how you inform router 1 about the remote network. So don't worry about this. We are going to do our home. We are going to build the network and then demonstrate it. Any question on that before we proceed? And vice versa, we have to go to router 2 and also do the same thing for this remote network. That is when people here can begin to talk to people here. If not, they can't talk to themselves. Good. She said, you know, they finish you. Let me see the attendance today. Because at least there's so many things to remember. So that's why the attendance has been dropping. Today is not bad. So I will demonstrate this in the next class. I don't want to go into that one today at all. I will just talk today. The next class we fire on in labs. Okay. So let's proceed. So that is static route. What I just explained now is static route. What about dynamic routing protocol? Dynamic routing protocol are used by a router to automatically share information about the reachability and the status of remote networks. Even though we are still going to get involved briefly, we're going to set it up, but we'll leave the rest to the routers to continue from there. And that we are going to do when we start CCNA 3, not in CCNA 2. So the main difference between static route and dynamic is dynamic will continue from where you left, but static you have to keep on getting involved. Network goes on, you get there. Network comes back, you get back. Network goes on, you get there. Network comes back, you get there. So you have to keep on getting involved. Dynamic routing protocols perform several activities, includes network discovery and maintaining routing table automatically. You just set it up and leave it there. They keep on updating the routing table. Updating could mean removing a network or adding back a network, depending on what is happening. And what about network discovery? They automatically discover their neighbors, directly connected neighbors. They discover and they can exchange information about remote networks. So it doesn't matter the numbers of routers you have on your network. The moment you throw dynamic routing protocols at them like this, they will sort themselves out. And we're going to see the advantage of that when we go to our configuration. Look at this scenario right now. Show IP route, we've used that command before. We can see who simply means they are using OSPF. OSPF is a type of dynamic routing protocol. So this is a network here. This is another network here. These two networks are remote networks. And this router 1 got to know about them using OSPF, which is a dynamic routing protocol. And the same thing also applies to IPv6. When you see S rather, it means we are the one doing this manual configuration. When you see O, we are involved partly, but we leave them to sort themselves out later. Don't ever forget that. And we're going to demonstrate that also when we get to the next level. I've talked about default routes, where if you don't know you don't know where you are going to, the router doesn't know, it just sends this to the ISP, and that is configured on the edge router. And we're also going to learn how to configure the default route of both for IPv4 and IPv6. So that's that about static routes and dynamic routing. There is another terminology you're going to come across. It is called, I've mentioned it earlier, administrative distance. Administrative distance. What is the administrative distance? It is called the trustworthiness. Trustworthiness. See it here? Administrative distance represents the trustworthiness of the route. What does that mean? Sometimes your router will learn about a destination from two different routing protocols for whatever reason, especially the dynamic. If it's learning through OSPF, it's learning through AIGRP, it's learning through RIP. Which report will the router believe? Or even for us, we put static also. Which report will the router believe? The router needs to make a decision on the protocol, which protocol to follow, on which report to believe, when it's learning about a destination through different routing protocols, either static or dynamic. And what is going to use to break that tie to make that decision is administrative distance. In the administrative distance, there are different numbers by default. Look at static route, it comes with 1. Look at OSPF, it comes with 110. And look at RIP, it comes with 120. So if our router is learning something from static route with an administrative distance of 1, it's learning the same information from OSPF with administrative distance of 110, and it's also learning the same information from RIP with administrative distance of 120. It believes the report of any of the protocol that has the lowest administrative distance. The lower the administrative distance, the better the router believes the report. What if it's between RIP and OSPF? RIP is 120. It's a routing protocol, dynamic routing protocol. OSPF is 115. The router would believe the report of OSPF and use OSPF to make final decision, or use OSPF reports to make final decision. That is what administrative distance is used for. It is the trustworthiness of the route. And the lower the AD, the more trustworthy the route source. It's just an algorithm or something to determine which network to install in the routing table based on the administrative distance of the routing protocol. Because the router will not install all of them. It needs to only install one at a time. There are some of these routing protocol that can load balance. We're going to come to that. But the moment we have information from different routing protocols for the same destination, the router has to make a different decision. Is this clear? Clear. It's only Ali that responded. What about the rest? Okay. Good. So anytime, so now in our router, we saw administrative distance the other time. Let's go back to our router. Is he in the router? I think it's in the router. Show IP route. Oh, no, not here. I think it's on my slide. Now, why don't I have administrative distance here? The administrative distance of connected route is 0 for my own output. Connected route is 0. It's the best route so far. The router believes if I am directly connected, that's the report I'm going to believe. You can't tell me anything otherwise because it doesn't make sense. You can't tell me that to reach that network, I have to now pass through a different router. No way, I won't believe you. But what if it is a remote network? You got to use the administrative distance. If there are more than one, if there's more than one information, it has to break the tie. This is the administrative distance because we are using OSPF. This is pointing to the administrative distance. We are using OSPF. When you see static routes, you're going to see static route is going to be 1. Let me see if I got something like that here. I don't think I have any. Oh, I don't. When we do static routes configuration in next class, you're going to see. I don't have static routes here. So you're going to see that one is going to be 1. So if the router has more than one information from different routing protocols coming from different angles, it's just going to go with the routing protocol that has the lowest administrative distance. And these are different routing protocols that you have out there. Route source, you can see our route source directly connected. See it here, administrative distance of 0. Static route is 1. EIGRP summary route is 5. External BGP is 20. Internal EIGRP is 90. OSPF is 110. ISIS is 115. RIP is 120. External EIGRP 170. BGP is 200. And guess what? In CCNA, this is the only dynamic routing protocol we're going to talk about. Before, it used to be 3. We used to have RIP, and we used to have internal EIGRP, and then OSPF. But they've removed this and this from CCNA. This is the only one we're going to talk about as a dynamic routing protocol. So take note of this. Static and dynamic routing, I've been talking about them. What's the difference? Static and dynamic routing are not mutually exclusive. Rather, most networks use a combination of dynamic routing protocols and static route. Sometimes you have to use the two. It depends on what you are doing. It depends on what you are trying to achieve. Static routes are commonly used in following scenarios. As a default route forwarding packet to service provider, I've explained that one. For route outside the routing domain and not led by the dynamic routing protocol, if a route cannot be led by the dynamic routing protocol for whatever reason, you can use static route to reach it. When the network administrator want to explicitly define the path for a specific network for security reason, this is good. And when you are routing between stub networks, static route can be used for all of these, and you can combine. Static routes are useful for smaller network with only one path to an outside network. They also provide security in a larger network for certain type of traffics or links to other networks that need more control. So for security reasons, sometimes, even though dynamic can work for us, we can decide to go the way of static. Dynamic routing protocol are implemented in any type of network consisting of more than just a few routers. Dynamic routing protocol are scalable and automatically determine the better route if there's a change in topology. Dynamic routing protocol are commonly used in the following scenario. A network consisting of more than just few routers, that's for big network. When a change in the network topology requires a network to automatically determine another path. If you are load balancing, we can load balance on static route too. We can, but it's better off on dynamic routing protocol. And for scalability, as the network grows, scalability in networking simply means ability to grow. As the network grows, the dynamic routing protocol automatically learns about new networks from their neighbors. That is why this is preferred for big networks. So you can see the table showing the comparison between the two of them. Just all these things we just explained now, dynamic routing protocol and static routing protocol. When you talk about configuration complexity, this one, independent of network size, no shaking. This one, your work increases with network size. What about topology changes? It automatically adapts to topology changes. This one, administrator intervention is required. Scalability. This is suitable for simple to complex network topology. This one is suitable for simple topology. When it comes to security, under dynamic routing, but you must configure its security into it. But this one is integrated. Resource usage uses CPU, memory, and link bandwidth. That's for dynamic. But this guy, no additional resources is needed. When it comes to path predictability, knowing where you want to go, route depends on topology and routing protocol use. But here, we define the path to destination. Sorry. We define the path back to destination. And all of this comes with experience as you continue in your career. But for CCNA level, at least you should master everything that has to do with all the kinds of static routes. I think there are 3 or 4 of them, which I said we're going to take care of next class. Then you master one OS, the only OSPF is CCNA3. Then you are good to go for now. As long as you can do OSPF, you can do RIP, and you can do EIGRP. RIP has been discontinued. The EIGRP is still out there, and they talk about it in CCNP. So this is the evolution of dynamic routing protocols. There are others that they've discontinued completely. EGP, IGRP, RIP version 1. Look at when they built those protocols. Then from 1990, we have others, ISIS, OSPF version 2, EIGRP, RIP version 2, BGP, RIP new generation, the BGPMP, OSPF version 3. Then from 2000, we now have ISIS version 6. ISIS is a protocol used by service provider and BGP. These two are referred to as exterior gateway protocol. They are used by service provider. But don't forget, we are going to just do this one and this one when we're talking about dynamic routing protocol. So these are the protocols again here. Some of those protocols are referred to interior gateway protocols because they are used within an autonomous system. What is an autonomous system? Collection of networks that belong to the same organization. They may be in different cities, they may be in different countries, but they belong to the same organization. So these are dynamic protocols. This is dynamic routing protocol used within an autonomous system. Whereas there are others that are called exterior gateway protocols. They are used on the internet or between different autonomous systems. When one company wants to connect to another company, they want to connect to themselves to do business together. You use exterior gateway protocols. So look at the interior gateway we have for IPv4. We have RIP version 2. We have EIGRP. We have OSPF we have ISIS. This can be contested anyway, because this used to be under exterior, this ISIS. Then for IPv6, we have RIP new generation. Then we have EIGRP for IPv6, and then we have OSPF version 3. They further break these things down. They classify the interior gateway routing protocol. Some are called distance vector. You will know why when we get there. The others are called link states. So these ones here, RIP and EIGRP are referred to as distance vector. And OSPF and ISIS are called link state. But either way, all of them are referred to as interior gateway protocols. They are used within an autonomous system. And of course, we have our exterior gateway, which is BGP for IPv4, and then the BGP for IPv6. And the BGP, those BGP ones, they are called path vector routing protocols. All of these things, they are loaded on their own. They are loaded on their own. Most of these things you do them in CCNP, and then the rest you do in CCIE. So we can just touch them. We can't go into the depth of that. But BGP is used mainly for network. Ali, can you hear me? Dr. Samuel, can you hear me? Okay.
Not too loud, sir.
Not too loud?
I can hear you.
Okay.
I hear you.
I don't think it's from my side. Okay. So BGP is used by service providers between service providers. But these are not things that are covered in CCNA. You learn about BGP more in CCIE. A little bit of BGP in CCNP, but more of it in CCIE. So we just need to be aware of that. So dynamic routing protocol concept, what do they really do? They use algorithm to decide on where the message will go to. A routing protocol is a set of processes, algorithms, and messages that are used to exchange routing information and populate the routing table with the choice of best paths. The purpose of dynamic routing protocols includes the following: discovery of remote networks, maintaining up-to-date routing information, choosing the best path to destination network, and ability to find a new best path if the current path is no longer available. All of this, we're going to learn them under OSPF. But in our next class, which is going to be the last class, is only static route we are going to do. And then we'll wait until the OSPF class, that is CCNA 3, before we implement this or demonstrate this. But that is basically what your dynamic routing protocol will do for you. It's better than static, especially if you have a big network. And we're going to also check the routing, the data structure of dynamic routing protocol. All of this, we're going to talk more about this in CCNA 3. How it's able to discover neighbors, how they exchange information with neighbors, what kind of algorithm they run to discover to make decision to go to destination, and all of this is we're going to talk about then. And different routing protocols use different algorithm to make decision to go to the destination. Like RIP, for instance, it only considers the numbers of routers on the destination, on the way to the destination, which is very stupid because it doesn't use bandwidth. This is what I'm trying to say. For instance, now, let's say we're going to this destination now. This is a switch here. Let's see, this is connected here, this is connected here. So this router will say, okay, if I'm going through this path, there are two routers, 1, 2. If I'm going through this path, there's only one router. If you are running this particular dynamic routing protocol, it believes that this path is the best, even if this is the fastest route to destination. Maybe that place is 10 gig and this place is just 100 Mbps. So RIP doesn't make a good decision. It doesn't consider the speed of the network to make decision. So different routing protocols use different metrics also. Metrics. They've considered different things to make decision on the path to go to destination. But we're not going to go to RIP, but we're going to consider OSPF. And these routing protocols, some of them have the ability to load balance, some don't have the ability to load balance. Some can load balance by default. Some we have to make them to load balance by configuration, because you may want to achieve that. What do I mean by load balance? We should know by now. We've done spanning tree. What some routing protocols can forward the message through router A, some people are going through router B, like that, like that, like that. Some are going here, some are going here, some are going, some are going, some are going, some are going here. That is ability to load balance. Some can load balance, some of them cannot load balance. When a router has two or more paths to a destination with equal cost metrics, that is, the speed is the same, then the router forward the packets using both paths equally. This is called equal cost load balancing. The routing table contains single destination network, but multiple exits interface, one for each equal cost path. So if the speed here, I'm using speed most of the time, that's not the only thing that is used to determine the best path to the destination. Latency is also there for some routing protocol, but layman's language, speed or bandwidth is the best. So it will say, okay, to get to this particular destination, I can pass here, I can pass here. If the cost is the same based on speed, it will put both the two exits, rather, that's the two next up, in its routing table, and it can begin to load balance between the two routers. So the routing table contains a single destination network, but has multiple exit interfaces, one for each cost path. The router forward package using the multiple exit interfaces listed in the routing table. If configured correctly, load balance can increase the effectiveness and performance of the network. Watch now. Equal cost load balancing is implemented automatically by dynamic routing protocol. Equal cost. What if the cost is not the same and we have two different routers to the destination? It is enabled with static route. We can make that one happen also on static route. When there are multiple static routes to the same destination network using different nets of routers. So this load balancing we are talking about, we can also make it happen on static route, but that is if the cost is equal. But then sometimes, even when the cost is not equal, the only routing protocol that can support unequal cost is EIGRP. When I say unequal, maybe to go to destination through here, the cost is say 10. To go through the other side, the cost is 9. This is no longer equal. EIGRP can be configured to load balance across unequal cost path. Other routing protocols cannot do that. Even static route can do that. But for EIGRP, you can configure it to do that. So that is it for today's class. Any question? So we spend almost 1.5 hours. Yes, doctor.